Okay, so I think the purpose of this lecture is to put everything into one coherent strategy, right, of the techniques for series testing, whether it's convergent or divergent. So essentially, it's just kind of my thought process, how I might go about doing these types of problem. All right, so we're gonna have a giant flow chart here. Let's be ready for it. So standard question: given infinite series, is it convergent, divergent? So the first thing you should think about is to ask yourself, does it resemble a p-series? Okay, so are you a p-series? So what is the p-series? So it has a very specific form. Kind of the standard example that we should know. Well, it's the infinite sum n equal to 1 to infinity of 1 over n to the p. So for this infinite series, it's going to be convergent. If p is bigger than 1, strictly bigger than 1, it's going to be divergent if p is less than or equal to 1. Okay, one of the most standard examples we went through. Now, if you're not a p-series, then you should ask yourself, are you a geometric series? Okay, so geometric series. So what does geometric series look like? I think it's bigger. So geometric series is going to be a bunch of terms, right? A plus a r plus a r squared plus a r cubed and so on. So we're gonna use a sigma notation for that. Starting from 1 to infinity. A times r n to the minus 1, r is the common ratio. So if the series is convergent, we actually get a very nice result, right? If it is convergent, we know it's going to be equals to a over 1 minus r. So this is true when the absolute value of r is less than 1. So maybe it's a little bit bigger. Less than 1. Strictly less than 1. It's going to be divergent if the absolute value of r is bigger than or equal to 1. Okay, so here we're going to assume that a is non-zero. If a is 0, it's not very interesting, isn't it? You're going to be adding a bunch of 0. Alright. So if you're a p-series, you're done. If you're the geometric series, you are done as well. Now, it is a necessary condition that all the term as n approaching infinity is 0. So maybe I should be asking myself that question. So is a limit as n approaching infinity a sub n equal to 0? Okay, well, just put question mark. So this is sort of the first major test, right? Is the divergence test. Some people also call it the nth term test. Okay, so divergence test. What is it? Divergence test. Well, the limit as n approaching infinity, a sub n. If it's not equal to 0, well, then it's gonna guarantee that this infinite series is gonna be divergent. Absolutely, it's for sure. Tell us nothing about the convergence of the series, but if the limit of a sub n as n approaching infinity is not equal to 0, then we can be pretty sure that this thing is going to be divergent. Now, what's the condition for this one? Right. So remember that we always have some sort of conditions flying around when the types of series testing. So what's the condition for the divergence test? Well, actually none. So it's actually very nice. So if it's divergent, then nothing you have to check for. Okay. So conditions, none. Alright. Now after this, right, there are two possibilities. So the majority of our tests will fall into the category where all of the terms will be positive, right? So you should ask yourself after this, so if it is equal to 0, so if you after you do this test, you take the limit as n approaching infinity of a sub n, and it's equal to 0. So if that's the case, right, then it could be convergent or divergent. So ask yourself the question, so for the first case, are the a sub n term bigger than or equal to 0, right? So the majority of our cases will fall into this category. So the first major test, well, what is it? The integral test, right? So for the integral test, you want to ask yourself, is then f of x such that it's easily integrable, right? And we can model that function in a reasonable way. So is there an f of x such that let's say can I model that function by some, can I model that sequence by some function, rather? Okay. And 2 is f of x easily integrated. If the answer is yes to those questions, then we can use the integral test. So the integral test. Well, what is it? So the infinite series from n to 1 to infinity of a sub n. So this is going to be convergent. If and only if, right, the improper integral 1 to infinity of f of x dx convergent as well. Okay, so it goes same for the divergence case as well. Right, so this is nice, right? Because using the test, right, I could do the improper integral. Thus, we can use calculus to show convergence or divergence. So what are the conditions for this test? So this one, we have to check conditions, all right? So almost all of my cases gonna be eventually. Got to be true eventually. Maybe I should put that there, so eventually. So you want f to be decreasing. You want f to be positive. You want f to be continuous. Technically, you don't want, you don't really need f to be continuous. The reason they put it in the book is because you want thing to be integrable, right? It's continuous, and you be able to integrate. But actually, if the function is decreasing, so it's sort of implied the integrable function. And actually pretty sophisticated theorem, so we're not going to worry about that. So we're going to follow the book for now. All right. So that's conditional integer. Now, what if it's impossible to integrate? What do we do? Well, we got to think of other tests. So the next two strategy, pretty important one, are the comparison test, right? We have the standard comparison test, and we have the limit comparison test. So let me put them side by side. So these two are pretty important. So we have the comparison test, the standard one. So, so what should we be asking ourselves? Huh? So the idea of comparison test is to compare your infinite series to some series that we know the answer to, right? And we know the answer to the P series and the geometric series, right? So you want to ask yourself then, does the series resemble the P or the geometric series? Okay. So I want to ask myself, does the series resemble the P or the geometric series? Geometric series. So if the answer is yes, then we have two options. We're going to use either the standard comparison test, or we can do the limit comparison test. Now, you want to pick the standard comparison test, right? If a of a sub n is easily bounded. Okay. So answer the question: can a sub n be easily bounded? So if it's yes, then we want to do the user comparison test. So what is it? So we have the infinite sum from n equal to 1 to infinity, b sub n. Now, so for the upper bound comparison, if we compare it to, let's say, a series b sub n, and we know a sub n is less than this thing. Okay, so if b sub n is convergent, well, it forces a sub n to be convergent as well. Okay. Now, what about divergence? So for that, right, if b sub n is divergent, then I know nothing about a sub n. So for that case, we need to have a upper bound for for A sub n. So let's say we compare it to some series, let's say C sub n. And we know that C sub n is divergent. Now, if the series A sub n is bigger than or equal to C sub n, and C sub n is divergent, well, then it's going to imply that A sub n is divergent as well. Okay, so the condition really you want to have some sort of bounds for A sub n. So again, eventually, so for the first case, you want to have a upper bound for A sub n, so you want to bound A sub n by some infinite series B sub n. Okay, so if B sub n is convergent, then it forces A sub n to be convergent. For the second case, if I can bound A sub n by some lower bound C sub n, and I know that C sub n is divergent, well, if the smallest series is divergent, then the bigger one got to be divergent as well. So there we are. So when I say can A sub n be easily bounded, right? It implies that, can we write out this? Like, can we easily find a bound for this one? Okay. If we can, write out immediately the bound or thinking not too hard, then you want to use your comparison test. But if we cannot find such bound easily, then you might want to do the limit comparison test, right? It's going to be a good candidate for us. Limit comparison test. So what is it? Well, you want to take the limit as in which infinity of the ratio A sub n over B sub n, say it equal to some number L bigger than 0. Now if this happens, right, well, it forces the following thing. If the infinite series of A sub n is convergent, well, then B sub n got to be convergent as well. So it works, go both ways. So the same thing for divergence, right? If one is divergent, then the other one got to be divergent as well. So conditions. Well, the condition about this is you want both A sub n and B sub n to be bigger than 0. Alright. Now, another test that we have seen was the ratio and the root test. So that you want to do the ratio or the root test if we have some sort of factorial or something raised to some power of n, right? If that's the case, then I want to use the ratio root test. So they're pretty similar, so I'm going to put them into 1. So let me put the question here. So I want to answer, so does an have factorials? Something like factorial, right? Is an in the form of some sequence raised to the power n? Okay. If the answer is yes, then we want to do the ratio root test. Ratio root test. Might need to make this a little bit bigger. Alright, so it's pretty standard. Asking the limit as n approaching infinity of the absolute value of a n plus 1 over a n. This ratio test, well, for the root test, it's going to be the nth root it's going to be the nth root of the absolute value of an. So say equal to some number L. Now we have three possibilities, remember? If L is less than 1, well, then we know this is going to be absolutely convergent. Pretty strong condition. If L is bigger than 1, well, we have divergence for that. If L goes to 1, well, whatever goes to 1, then what happened? Well, we have, it's going to be inconclusive, isn't it? Cannot tell. Inconclusive. Can't tell. So what's the conditions for this? Actually none, right? It's actually the nicest possible test that we can do. If we can do the ratio through test, then you have nothing to check for. Okay, so like I said, none. Okay, so this is you're going to apply these tests if all your terms are bigger than or equal to 0. Now, actually, the ratio root test also work for the negative term as well because we're taking the absolute value, right? So we're gonna, talk about that right now. So if all of the terms are positive, bigger than 0, then we want to use this strategy. Now the other case, well, what if I also have the negative term in there? So what do we do? So if you have plus or minus term in the series, then so let's use this first question. Are you plus or minus? So we know one possible outcome is we're gonna be an alternating series, right? So I just have this after that, right? Are you an alternating series? If the answer is yes, then I can do the alternating series test. So I can do the alternating series test. Well, let me bake the condition into this one as well. So I need all of the term to be decreasing, right? The absolute value. I need the limit as n approaching infinity, a sub n to be equal to 0. So if we have these two conditions, then, well, my alternating series is convergent. So pretty weak condition. Convergent. So what's the condition? Well, the condition you need to be an alternating series, right? If you're not an alternating series, then you're gonna do this test. So it's kind of obvious. So conditions. You have to have the form of something like minus 1 to the n minus 1, right? Because I want to be alternating between negative and positive. Sometimes you can also have negative 1 to n, depends on the context of the problem. And you want c sub n to be bigger than or equal to 0. Okay, so less than 0, not going to be alternating that very well. So if it's satisfied the condition, then you have an alternating series. Now, what if we have positive and negative term and it's not strictly, between those terms, right? You can have something like plus 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 and then negative negative negative, right? So in that case, you don't have an alternating series, even though you have plus and negative, right? But it's not alternating between plus and negative. Well, if that's a situation, then your only choice really is to show absolute convergence, right? So have no option but to show absolute convergence. So we want to, so what is it? Well, want to show, instead of a sub n, you want to do absolute value of a sub n. So does the infinite series of absolute value of a sub n convergent? Okay. If it is yes, then I can do these tests here as well. So I would say the worst possible case that you can have is when you have not an alternating series and you are conditionally convergent, right? Then you wouldn't be very sure what to do, because that's the worst possible scenario. Wouldn't really turn up, so you don't have to worry about that. All right, so this is pretty much it. Really, truly, of the possible in the future. Next undergrad, it's gonna be able to decode it using this flowchart. All right. So I think we should do some example, sort of go through every possible cases here. So just gotta be ready. Let's do some example. Let me copy this thing first. So we're just gonna follow through this kind of flowchart here. I'm gonna go through every possible leak that can happen. All right. So example 1. Go to new page. So we have infinite series of 1 over n squared plus 1 over 2 to the n. Standard equation, convergent, divergent. So the question is convergent, divergent? Well, first thing is it P series? Well, yeah, I do see the P series in there, right? The 1 over n squared, but it's not just the P series, right? We also have the geometric series as well, right? The 1/2 to the end there. So so maybe I should ask myself independently whether the 2 is going to be convergent. Well, so let's do that. So independently, I know that 1 over n squared is convergent because of the P series. And I also know that the 1 over 2 to the n also convergent because the common ratio is 1/2, so it's going to be less than 1, so I know it's going to be convergence by the geometric series test. So we have the sum of two convergent series, so that's the sum of them will be convergent as well. Okay. So this implies that the original series that we have got to be convergent if the sum of the two series inside is convergent. Alright, so we stop there. We need to go further. Alright, so let's do another one. Let's say 1 to infinity. So square root of n squared plus 1 over n plus 1. It's convergent. Divergent. I have to paste the dang it. That's not what I want to do. And copy this again, no big deal. Sorry about this. Alright, again I want to use my flowchart here. I'll walk you through the possible scenario, realize erase this thing. Okay, so again, as so is this a P series? No chance. Is it a geometric series? Not a chance. Can we do the divergence test here? Well, it looks like an algebraic function, right? But if I decided to take the limit as n approaching infinity of this guy, actually not that bad, right? So let's do it. So if I take the limit, as n approaching infinity. It's one of the standard limit problem, really. Well, the answer is going to be dictated by the bigger front term, right? So I'm going to chill it a bit. You can divide both sides by n squares, but I'm just gonna. It's kind of obvious, so it's going to be equal to root n squared over n, right? Dictated by the front term, the biggest term. And this one is just equal to 1. Okay, n over n is 1. 1 is non-zero. Well, that's the conclusion then. Well, by the divergent test, this infinite series got to be divergent. That's the result. Okay. Let's do another one. Say we have cosine and pi over n, convergent, divergent. So I'm sorry. So what do we do? So again, as you said, it's another question, right? It's a P series. Yeah, kind of, right? Have that 1 over n there, but the cosine of n pi kind of forces not to be a P series. Geometric series, no chance. Can we do a divergent test? Well, 1 over n. 1 over so as n approaching infinity, 1 over n is going to be equal to 0, right? Cosine is bounded, so we get 0. So not going to be very useful here. Now we know the cosine of n pi is going to be oscillating between plus and minus, right? Cosine of pi, cosine of 2 pi and 3 pi and so on. Could get minus, plus, minus, plus. So we get to here. So I think it's actually an alternating series, isn't it? So I can do so hopefully we can do the alternating series test. Okay. So again, Just a couple of observation. Cosine of n pi is -1 to the n, right? So this implies that we have an alternating series. Alright, so the condition, well, we know 1 over n is decreasing, pretty obviously. And the limit as n approaching infinity of 1 over n is equal to 0. So D2 implies that the original series cosine n pi divided by n are convergent. Okay, by the alternating series test. Alright, nice. Let's do another one. So the infinite series from n equal to 2 to infinity. We can start at 2. It doesn't matter, right? Make no difference fundamentally. To say 1 over n times ln n. The reason I'm starting at 2, right? So that I don't get 0 on the denominator. So again, convergent, divergent. Same question. So let's paste that flowchart here. Now, so again, as I said, same question is P series, no chance. Geometric series, not really. Can we do a divergence test? Man, as n approaching infinity, right? I mean, 1 over n, ln n is gonna be getting to infinity as well. So we're gonna get 0, so not gonna be very useful. So is everything gonna be bigger than 0? Yes, because ln n is gonna be positive from 2 to infinity. So now at this stage, what do we do? Comparison test, root test? Not really. I guess we can. It's kind of resemble the P series, isn't it? But then the ln of n is gonna be kind of problematic for us. Root test, ratio test, not really. Don't see any factorial or n power. So really the only choice here is to do the integral test, right? So, 1 over x ln x doesn't seem that bad to integrate if I do a substitution. Use substitution, I let u equal to ln of x, right? So hopefully the integral test works out. So a couple of observation, right? X ln x bigger than or equal to 0 on this interval from 2 to infinity. And it's increasing, right? So this implies that 1 over x ln x is going to be bigger than 0 and decreasing on 2 to infinity. So I can apply the integral test. Alright, I'm not going to go through every single detail of this problem, right? It's going to take a lot of time. But the key point is just how we're navigating through these techniques. Which one should we pick? Optimal options. So we have to do the improper integrals from 2 to infinity of 1 over x ln x. Now this equal to the limits of t approaching infinity. 2 to the t, 1 over x ln x. So if you let u be ln x, it's gonna unravel the whole thing, and you're gonna get the limit as t approaching infinity of ln x from 2 to t. So this equal to t approaching infinity of ln absolute value of ln t square minus ln absolute value of ln of 2. So this thing is gonna be so ln infinity is gonna be infinity, so it's gonna be infinite. Well, by the integral test, it's gonna be, well, divergent. Okay. All right, nice. Let's do another one. So 5, let's say we have let's say we have cosine n over n cube. All right, convergent, divergent. Solve same question. Well, P series. Oops. P series, not really, because of the cosine of n. Geometric series, no chance. Divergent test, not gonna work because cosine of n is bounded, and the limits of n cubed is gonna be 0. So everything gonna be 0, or we have plus and minus. Well, it's gonna be plus and minus, right? Because of the cosine of n there. Now it's an alternating series. Not quite, right? Because even though, cosine of n is going to be plus and minus, but it's not strictly oscillating between plus and minus, right? It's going to be like plus, 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 and then negative, negative, and so on. So we have no option here but to show absolute convergence. All right. Now, once you get to this step, right, what do we do? Integral test. Oh, it's going to be a nightmare integrating this guy, so I don't want to do that. Ratio root test. I mean, we have the power there, right? But then I don't want to deal with something like cosine of n plus 1 over n cubed. It's kind of a nightmare to do as well. So maybe, my only option is to do some sort of comparison test. All right. So I have the n cubed there. So it does resemble the P series, right? So I could probably do the usual comparison test, compare it to the P series, 1 over n cubed. Okay. So let's try that. So the absolute values, well, first of all, some observation. We can bound this thing above 0, so the absolute value of cosine of n over n cubed. I can bound it by 1 over n cubed. Okay. So this thing, the absolute value of cosine n over n cubed, is going to be absolute convergent. By the comparison test, right? Well, if it is absolute convergent, then the original series is going to be convergent as well. It's going to be convergent. All right, nice. Okay, so for this one, we want to use a standard comparison test, right? Because this can be easily bounded by 1 over n cubed. Okay, if it's kind of tough to find the bound for this, right, then you might want to do the limit comparison test. But luckily for us, it can be easily bounded by 1 over n cubed. So we're going to stick to the usual comparison test. Let's do 2 more problems. Let's do 7. Actually, 6. I haven't get to 6 yet. Say with something like sine of 1 over n. Standard question, convergent, divergent. So look up the places here. So is this P series, no chance, have the sign outside there. Geometric series, no chance. Divergent test, well, as n approaching infinity, 1 over n is going to be equal to 0. Sine of 0 is going to be 0, so not going to be useful. So is every term is going to be positive? So yes, so what do we think? Well, should be positive, right? Because 1 over n, so it's going to be less than 1 over n is going to be less than 1. So we're looking at sine of something less than pi, so it's just going to be positive. Alright, so now which one do I want to do? Integral test? Oh, not a chance. I don't want to integrate sine of 1 of x. Can I do some sort of ratio root test? Not really. Does it have any factor? Does it have any n power? So nope. Can we do it? So now got to do comparison test, isn't it? Now which one, right? The standard one or the limit comparison test? It's kind of hard to bounce sine of 1 over n, isn't it? To any kind of p series that I know of. So maybe my best option here is to do a limit comparison test. Okay. So conditions, well, we know sine of 1 over n. 1 over n is going to be bigger than or equal to 0. For all n, now recall a few things. Remember that the limit as x approaching 0 of sine of x over x equals to 1, right? One of the standard limit example in first semester. So this is going to be very useful for us because this implies the limit as n approaching infinity of sine of 1 over n over 1 over n got to be equals to 1, right? So by the limit comparison test, the infinite series of sine of 1 over n got to be divergent. Okay? Because of the infinite series of 1 over n is divergence. Okay. So again, is it not clear? So this is divergent because the infinite series 1 over n. This is the harmonic series. Remember, divergent. Whoops. Dang, I'll get rid of this. Because the infinite series 1 over n is divergent, right? Harmonic series on the kind of this core example. So this is true by the limit comparison test. Very nice. Let's do 7. This is kind of interesting one. Let's say we have n factorial over n to the n. It's convergent. Divergent. So again, ask ourselves this. UP series? Not really. Geometric series? Nope. Divergent test? Actually very tricky, right? Because n factorial grows pretty fast, so is n to the n. So we cannot tell really whether it's going to be equal to 0 or not. So maybe I should just press on for this. Everything positive? Yes. So get to this step. Now integral test, no chance. I don't want to integrate that. What is x factorial, right? What does that even mean? X factorial. That actually means something, but actually pretty sophisticated, so we're not gonna worry about that. P series, geometric series, not really. So really, my only option is the ratio root test. To be more precise, the ratio test, right? Because I have the n factorial So let's do it. So the a sub n term is gonna be n factorial over n to the n. So if I do absolute value of a sub n plus 1 over a sub n, well, it's gonna be some nasty algebra. Well, actually not too bad. So that's gonna be equals to, well, n plus 1, right? Because n plus 1 factorial over n factorial is gonna give me n plus 1. So that's that piece, and now we have n to the n over n plus 1 to the n plus 1. Okay. So this implies summable algebra. This implies that a sub n plus 1 over a sub n is equal to n plus 1 to the n. Okay, so we just deal with the n plus 1 terms there. Now this is kind of nasty, isn't it? N to the n over n plus 1 to the n. So what I'll do, I'll just put the nth power to the outside. Still kind of nasty. Now again, I will do something kind of weird. I'll do n divided by n plus 1 divided by n to the n. Alright, still same thing. It's kind of weird, really written down. So now I could simplify the denominator a little bit. N over n is going to be 1 plus 1 over n raised to the n. 1 to the n, which is 1. Okay, so now recall something from first semester as well. Remember that the limit as n approaching infinity of 1 plus 1 over n to the n is equal to e, right? Rather remarkably. So this implies that the a n plus 1 over a n absolute value is going to be approaching 1 over e, right? This thing is approaching e. So 1 over e is less than 1 as n approaching infinity, right? So then by the root test, our original series is going to be convergent. Very nice. Convergence. Done. Okay. So actually, it shows something kind of nice as well. So it's kind of sort of aside for a moment. So this also implies that the limit as n approaching infinity of n factorial over n to the n is equal to 0, isn't it? So we cannot show that before, right? It's kind of unclear. But by this kind of absolute convergence, this very strong condition, it forces this to be equal to 0. So it's actually very nice. But you don't need to worry about that, but we actually show it actually got to equal to 0. Didn't know that before, but now we do. Alright, so last example. So it's like something like minus 1 to the n, 2 to the n plus 1 over 3 to the n plus 1 to the n. Seems about right. Convergent, divergent. Is it the usual testing? P-series, not really. Geometric series, no chance. Divergent test, actually I don't know. So yeah, so cannot tell really. So we have minus 1 to the n, so we know for sure it's going to be plus and minus in there. Okay, plus and minus. So is it an alternating series? Yeah, I think so. Wait, is it minus 1 to the n? But then you got 2 to the n plus 1. Yeah, so actually can't tell. right? We don't know whether it's gonna be absolutely oscillating between plus and minus, right? So actually we don't know that. So maybe my only option is to show absolute convergence. My only real option here. Okay, so now when we get to here, what do we do? Well, integral test, does it apply? No one wants to integrate that, right? Comparison test, I don't think there's a way to bound this thing. So I think the only option is to do the root test here, right? We have something to the end. So root test seem to be in order. So my a sub n term is minus 1 to the n. This is 2 to the n plus 1, 3 to the n plus 1 to the n. So the root test, nth root of absolute value of a sub n. So if I take the absolute value, take the nth root, we simply have 2 to the n plus 1 over 3 to the n plus 1. Okay, so I guess we could divide top and bottom by 3 to the n, right? Divided by the biggest term. So 2/3 to the n plus 1/3 to the n. 3 to the n divided by 3 to the n is just going to be 1. 1/3 to the n as well. Well, now the limit as n approaching to infinity of the nth root of the absolute value of n, a sub n, is going to be equal to, well, every single term is less than 1, right? So this is going to be approaching 0 as n. Oh, not this guy. This guy's 1. So don't touch that guy. So this one going to be 0, 0, 0. So we get 0 over 1, which is 0. 0 is less than 1. So, by the root test, the absolute value, I mean the infinite sum of 1 to infinity of minus 1 to the n, 2 to the n plus 1 over 3 to the n plus 1 to the n, well, it's absolute convergent, then it implies it's going to be convergent. Very nice. So this is it. Every single possible problem that you see in the future you should be able to navigate through it using this kind of flowchart. It's kind of intimidating, at first, this flowchart, right? But once you internalize it, it's going to do a world of difference to your understanding of series. So take your time to absorb this, right? Do a lot of the problem, kind of go through the kind of thought process that we did here, right? It's going to be extremely powerful tools that you can use in the future. All right.